Mr. Hayes, we're here with another AP Statistics video, and in this one we are going to look at the formula packet that you will have with you during the day of the exam. The purpose of this video is to help you feel more confident, let's just say 95% confident, that you understand where to look in this formula packet and how to apply these formulas during the day of the exam. So before we start this video, make sure you have with you a pencil, different colored pens, highlighter, and even your calculator, because we're going to kind of see some things that you have to be familiar with how to use them. So now let's dive right into the descriptive statistics part of the formula sheet. So here we are on the descriptive statistics part of the formula sheet, and you can see right away you get to cross out two formulas. Well, technically three, but you get to cross out two formulas. You get to cross out the formula for the mean, because you're not going to be expected to use that formula. And the formulas when it comes to standard deviation right here, you can cross those out, but don't cross them out big and thick, because you're still going to be expected to interpret the standard deviation. So do be aware, if these formulas help you understand how to interpret it, then just gently cross them out. But right away, we can forget the first two formulas in the packet. Now, the next set of formulas deals with the least squares regression line. And you can see I have some of them highlighted or really grouped together so you can understand what's going on. But let's start with the equation. It's your prediction equation, hence the hat above the y. So make sure when you're using it, you define your variables. If you're going to use y hat, if you're going to use x, you want to make sure you say, what does y hat equal? What does x equal? Or you can just use the variables in the equation to make your life a little bit easier, which is kind of what we've taught you. But you see how it's highlighted there, which means let me follow the highlighting. And as I follow the highlighting, it's grouped with this set of equations. Now, these set of equations are very, I'd say, rare to use. Most likely probably going to be on a multiple choice problem or a quick part of a free response. But a lot of times we forget about these. And I'm not telling you, do not cross them out. Do not cross them out at all, because you will still need to use them. And here's how they are used. They are used to find B and then A for the least squares regression line when you're given summary statistics. If you're given x bar and y bar for explanatory and response variables, and even their standard deviations, s sub x and s sub y, you can use those to help us find the parts to create our prediction equation. So we can use them to find b then a to help us write the equation for the least squares regression line, or we can use them to find r if we know what the slope is and what the standard deviations are for the explanatory and response variables. Now you can see, don't cross them out, but realize those two go together and they create the prediction equation over here. So that's why I have them highlighted. Now here's an example of what it would look like. You would be given what is x bar, what is y bar, what is s sub x, what is s sub y, and you would even be given what the r value is. And what you do is you find the slope first. You find what's b by plugging it into the r times s sub y over s sub x. And you solve for b, and we get our slope. And in this case, wow, it was an easy example. It worked out to be 3. And then the other one, I use the y bar equation. You know, y bar equals a plus b times x bar. And I plug in everything now because I now know b. So I can plug it in, I can solve for a, and there's my y-intercept, which allows me to write my equation. But I didn't define my variables, so be sure you define your variables. It's just meant to show you what this summary statistics would look like. You would get an x bar, you would get a y bar, you would get an s sub x, you would get an s sub y, you'd even get an r value there. So that is when you use those particular formulas on the formula sheet. And that's really going to be the only time you use these formulas on the formula sheet. Now, let's look at what's r. And so if I look at r in the descriptive statistics, that is a really nasty looking formula. And the good news is, you're really not going to be asked to plug into it. Now, if they're going to ask you something dealing with this formula, really it's going to ask you something dealing with transformations. How does R change if you increase all the x values by 10 and you double all the y values? What's the effect on R? I mean, that's how really this equation will be used on the AP exam. So don't cross it out. I would leave it there because it would help you mathematically see how each one changes by a transformation. If I plug every x value gets increased by 4, well, if I put an x plus 4 in for all of those, how does it affect the mean? How does it affect the observation? How does it affect the standard deviation? Same thing with multiplication. So I'm going to leave it there, but I'm going to know if I'm going to use that, it's because the exam is going to ask me, how does a transformation affect R? And that's really all you need from the descriptive statistics part of your formula sheet. We're now on the probability and distributions part of the formula sheet. And let's focus primarily on the two parts you see highlighted here, the purple and the green, the basic probability formulas. There is the probability of event A or event B, and you can see that in the purple here. And the U, you'd say for union, is the probability of event A plus the probability of event B minus probability of event A and B occurring together. That's the intersection, if you think of it like a two-way table. It's where the cells overlap. That's the and part of it. In a Venn diagram, it really is the overlapping part in the Venn diagram. So you're really looking at a very basic formula here. Is if you want to find the probability of two events occurring, you find the probability of each event occurring, and if they overlap, if they have an intersection, you need to subtract that so you don't count it twice. And that's really what that formula is telling you. The next formula you see in green here, that's a given that scenario. So what's the probability of event A occurring given that event B already occurred? And really that formula says, hey, find the intersection of A and B. Again, think two-way table. It's where those cells overlap with each other. Think Venn diagram. It's where they overlap with each other. Find that and then divide by the probability of event B. Because if A and B occur, what's the probability of event A given that B already occurred? So B is your total. So that's what we're going to be looking at, the outside part of a two-way table for event B. We can see a scenario if you want to think about it. Here's an example. Is if I have a standard deck of cards and I'm going to define my variables A as drawn an ace and H as drawn a heart. And if you've seen my videos before, you know I'm going to say, if you don't define your variables, you don't get to use them. And so if I want to find the probability of drawing an ace or a heart, I'm going to define each probability separately. Probability of finding an ace, 4 out of 52. Probability of drawing a heart is going to be 13 out of 52. But wait a minute. Is there any overlapping? Now, that's the ace of hearts. So I'm going to subtract 1 out of 52. And, of course, you really don't need to simplify, but I like to. So I simplified to 4 over 13. That's the basic application of the OR formula. Now, a given that for this scenario would be probability of A given that A decayed, which means find the probability of drawing an ace given that you already have a heart. So what's the probability of having an ace in my hand if it's a heart? I'm going to flip it over. Well, if I look at that, that's probability of an ace and a heart divided by the probability of a heart. Well, there's only one ace of hearts, and there's 13 hearts. So this probability is 1 over 13. This is a given that scenario. So these are the two basic formulas when it comes to probability. It's the OR formula, which kind of looks at the idea of take the two events, add them together, subtract any overlapping if there is, and you have the given that. Hey, event B has occurred. What's probably event A occurring given that already happened? So that looks at the overlapping of them, the intersection of them, the and of them, divided by the probability of event B. Now we're going to look at the meat of the formula sheet, where all these tables start, which is really dealing with kind of distributions. We're now on the probability distributions part of the formula sheet, and you can see we have three different types. We have discrete, we have binomial, and way at the bottom down there we have geometric. We're going to look at all three of these, but before, I want to talk about something I noticed when I was writing all these notes down is whenever we talk about distributions, we've always said you need to define the shape, the center, and the spread. I mean, that's not new. Here's what's interesting about this. Notice we do have the mean right here, center. We do have the standard deviation right there, spread. And if I look at this first column, primarily with the binomial and geometric, those are the shape of the distributions. So even when we define a binomial distribution, we still need to find the shape, binomial, the center, the mean, and the spread, the standard deviation. And the same for geometric. So even shape, center, spread is hidden on your formula sheet for you. A little hint. So discrete random variables. You're going to really be asked to look at the expected counts, is where you see the mean. And really that's telling you it's going to be laid out kind of like in a table, and you'll have different events, and you'll have the probabilities associated with each of those events. And what this formula is saying is, hey, take that event, multiply by its probability, take another event, multiply by its probability, dot, 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 all the way down, and add them all together, you're going to get the mean. That's really what that formula is telling you. We can also find the mean with our calculator, which, by the way, leads us to standard deviation, because you get to cross out that formula for standard deviation. You're not going to be asked to use that formula. However, that doesn't mean you're not going to be asked to find it, because you may. You're not going to be asked to interpret it, because you may be asked to interpret it. But how do you find it then if you're not going to use this formula? What you're going to do is you're going to use the lists in your calculator. So you're going to do one variable statistics. You can see the pictures down here. L1 is where you put the values. L2 is where you put their frequency or their associated probabilities. And so if we take a look at the screenshots from the calculator, is you can see my list says L1, my frequency list is L2, and then I'm going to go ahead and hit that calculate button and have it go ahead and spit out all the information I needed for it, the mean, the standard deviation, etc. However, be extremely careful, because you may need this list feature later on in the test. So you can see this caution here. Immediately after you use it, go back into one variable stats. You see that picture right at the bottom? Make L2 blank. Clear it out in that one variable stats. Because if you're asked to find the standard deviation of a discrete random variable on, let's say, multiple choice question 7, but you need this list feature on multiple choice question 32, well, you better delete that, otherwise you're going to get the wrong answer. So be extremely careful, as if you're going to use your list feature to find the standard deviation of a discrete random variable, afterwards, immediately afterwards, go back into one variable stats and clear out that frequency list part of it. So that is some advice for you as you're doing that. Now, the other two were binomial and geometric. So the difference, remember, between binomial and geometric is binomial looks at successes in a set number of trials. So you have a set number of trials and you're looking at successes in it. Geometric is how many trials until you get that first success. That's the main difference between binomial and geometric. Now, if you're asked to just find a probability associated with binomial, so right here we have the example. You have the probability of success, that's an S, is 0.8. Find the probability of getting 3 successes out of 5 trials. So we have a probability of success, we have number of successes is 3, we have a set number of trials. We have this notation, and really that first parentheses, that 5 over 3, do not put a fraction bar. That 5 over 3, no fraction bar, is the NCR. It's the number of combinations for it. And then that 0.8 to the third power is, hey, what's the probability of success? 0.8. How many successes are you looking for? 3. And then what is the 0.2? That's your probability of failure. Well, if you have 3 successes out of 5 trials, that's 2 failures there. And so you're going to use that, and that's really what that formula tells you. Or you can use in your calculator under distributions, because that's what it is, a binomial distribution, you have binomial PDF, P for points. It points to one particular thing, which is 3 successes. If you're going to use that feature in your calculator, be aware, just filling in the numbers, which it goes binomial PDF, and then you have your N, you have your P, and you have your X. So this would be 5, 0.8, 3, just writing down binomial PDF, 5, 0.8, 3, no credit. You need to define what each one of those spaces are in there. So if you're going to use this on a free response, what you want to make sure you do is put in the information. I'm going to put in here, hey, you know what? That is a 5, that is a 0.8, and that is a 3, perfect. Now I defined 5 is my number of trials. My success is 0.8, and the number of successes I'm looking for is 3. And so now that counts as your credit. So be aware, you can't just write down calculator talk. You have to define what each part of that notation is. So that is how you find that probability. Now let's go to center and spread for binomial distribution. And those are not hard to calculate. So if I look at this, finding the center is your number of trials times the probability of success. So if I'm doing 20 trials and the probability of success is 0.8, then multiply those, my mean is 16. Now if I want my standard deviation right here, I'm going to do the square root of number of trials times success times failure. And in that case, you can see my number down there that I get. Now, do be aware, and I can't really cover it in this video, but it's something to really pay attention to. Is you have so many standard deviation formulas, and you're going to see this as we continue, that it'd be nice for you to kind of focus on when you use which ones, because, hint, that's where some of the multiple choice selections come from, as little tricks of confusing the standard deviations with each other. Geometric. Now, that is how many trials until you get a success. Now, this is very easy to calculate. I wouldn't use my calculator for this one. I mean, I would just go ahead and say, hey, if the probability of success is 0.8 and I want my first success to be on the 4th trial, then that means I have failure, 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 success. So I have 3 failures and then finally the success. So that would be 0.2 cubed times 0.8. And we have our answer. So be aware that's how you would do geometric. Not too bad when it comes to it, but the phrasing is what you need to get you. And that's why this part is extremely important on the side, and I'll leave it here so you make sure you can copy it down while I'm talking, is the differences between binomial, successes in a set number of trials, and geometric way at the bottom here, which is the number of trials until you get that first success. So be aware of that. Now, to find the mean for geometric, good news is you have the formulas. It's 1 over the probability. So 1 divided by 0.8 is 1.2. Even the standard deviation of a geometric distribution is going to be the square root of the failure, 0.2, divided by the probability of success. And so we can see our setup there. So that is really the probability distribution part of our formula sheet. And you could hear some of the warnings, especially with that L2 list, about distinguishing the difference between geometric and binomial, and the general structure and format. The next part, we're going to look at the third part, which is the sampling distributions in inferential statistics, the big part of our formula sheet. All right, so we are looking at the sampling distributions in inferential statistics part of the formula sheet. And just a little advice here, these are the formulas, but what you plug into them are located on the next pages of the packet. So here's the structure, what you plug into the structure, you got to flip the page and see those formulas. So it's something that's not too friendly when it comes to the AP statistics formula sheet, but do keep in mind you should be used to these structures by now, so you might not have to rely too heavily on them, maybe just kind of a refresher. The first one we're looking at is a standardized test statistic, and that's your Z or your T. And the general structure of that is statistic minus parameter divided by standard error of the statistic. And really, you can think of it even, it's what we observed minus what we expected to see when it comes to the numerator part of it. The confidence interval, that is your statistic, plus or minus your critical value, which is your Z star or your T star, times the standard error of your statistic. And together, the product of the critical value and the standard error of the statistic is your margin of error. So remember, confidence interval, you're trying to capture the population parameter. So your statistic is in the middle, and then your margin of error on the right side and on the left side, they give you what the intervals are going to be. That's used for Z star or T star. The last one is your chi-squared statistic. That is the sum of what you observed minus what you expected squared divided by what you expected. That's the general structure. Now, to use the chi-squared statistic, look at that setup here, is really it's that whole, you do the first two plus ... plus the last one is kind of what you show down. And each of these highlighted parts right here, those are what you consider, what you contribute, or you might see it as components. And it might ask you, hey, which one contributes the most, or which component has the highest influence? Now, don't just say, it's this one because it has the largest number. Always specify direction based on observed minus expected. Is it a higher contributor to the chi-squared statistic because it was below what we expected to see? Or was it a higher contributor because it was larger than what we expected to see? Because we square them in the chi-squared statistic, all of those contributes are going to be positive. So we have to go back to the general plugging in to see, wait a minute, here's what we got for the contributor. Which Y? Is it below what we expected to see, or is it above what we expected to see? So again, always specify direction. But these are the general setups for your inferential statistics, all of them. These are the general setups for your inferential statistics. The standardized test statistic, statistics minus parameter divided by the standard error of the statistic, your confidence interval, statistic plus or minus your critical value, times the standard error of the statistic and your chi-squared. Notice, before we move on to the next pages in the packet, the statistic is highlighted a certain color. The standard error of the statistic is highlighted a certain color. Keep that in mind while you're marking, because I'm going to use that same color coding on the next part of the packet. So here we are on the second part of the packet, the back page of it, and really here's what you plug into the formulas on the front page at the very bottom. So be aware, and I do have them color coded again. The pink is the statistic and the green is the standard error. Now, something else to keep in mind is when we're looking at our decision-making tree, when we're going through that, we always have to ask ourselves first, are we dealing with a proportion, which, take a look at the top part here, there's your proportions, or are you dealing with a mean? And there's everything you have with means. So are we dealing with categorical variables, proportions, or are we dealing with quantitative variables, means? That's the first thing we have to ask ourselves. Now, what's the next thing we can ask is, well, hey, for proportions, how many samples do I have? Do I have a 1 sample or do I have a 2 sample? Look at that. That's the first column that you're dealing with. Oh, and then it goes into mean, center, and then standard deviation, spread. That's amazing. Now, what if it's means that we're looking at? Well, if we have this next, hey, I'm dealing with quantitative variables. Okay, good. So how many populations? 1 or 2? Well, I have 1 or I have 2, and I can go through those rows, but most importantly is this part. Do you know the population standard deviation, sigma, or do you not know the population standard deviation right here, S? So that's the breakdown, remember, when it comes to means, is before we go further, we have to ask ourselves, hey, do we know our population standard deviation, sigma, or do we not know it, which is S? And that tells us which to use. So those are the kind of the breakdown of the inference decision-making tree, really, and how it relates to your formula sheet. Now, another thing I have here are significance tests are highlighted in orange, and I also have the confidence intervals, because remember, that is what we're plugging into on the other page. You have your standardized test statistic, which is used to find the test statistic for your significance test, and you have the confidence interval here. So I do have to kind of break these down in that way. So you have your proportion, and really this part right here is, you could think of these two as your sampling distributions. Chapter 7 in a way, is that the mean of the proportions of all of your samples, so the mean of all the sampling proportions is an unbiased estimator of your population proportion, and that's what the first one says. The next one, notice here's your standard deviation formula for it. Now if we're going through, we have 1 sample here and we have 2 sample. And so keep this in mind, is if you're dealing with just a basic sampling distribution, here's what we're looking at. To find your z, you're going to take your statistic, p hat, minus your parameter, p, divided by the standard deviation of the statistic. And that's what we have right here for our statistic. However, we do need to keep in mind, what if we're dealing with a significance test? That's this part. If we're dealing with significance test and you have 1 sample, awesome. That's what you're going to do. But what if you have 2 samples? When you have 2 samples, it gets a little more complicated. Now, if you know the population proportions, it's right there. But you're not going to know those population proportions most of the time, especially with 2 samples, so that's where we do this. And so on this part of the formula sheet, notice it says when P1 equals P2. Isn't that kind of how we write our null hypothesis? So this part of the formula sheet is telling us where to go when we have a significance test for 2 sample proportions, and it's telling us how to calculate our standard deviation, and that is one thing to keep in mind, because that's that p hat sub c, the p hat of the combined sample proportions. You can see the formula down there on the bottom, and we have our standard deviation. Notice the structure of this formula right here. This structure is different than what you're used to seeing. Our formula looked like this, which is really the orange just distributing in the p hat, and the 1 minus p hat into the parentheses is really what we get there. But notice the formula on the formula sheet is slightly different than what you're used to using and used to seeing. So keep that in mind. This is, and I wanted to point it out, is it does say right up above, when P1 equals P2 is assumed, null hypothesis. Here's the formula for standard deviation. Wait a minute, there's a p hat sub c in there. What does that mean? Right below it, it tells you what p hat sub c means. So it's telling you where to focus if you're dealing with a significance test. Now, if I'm looking at the test statistic, here is the test statistic for it. It is the difference in your sample proportions. Remember, the order you subtract matters based off of how you define and what you're looking for. So you must state the order you're subtracting. If you don't define it, you don't get to use it. So you don't get to show the subtraction if you're not going to define the order you're subtracting. Now, normally, the null hypothesis says that P1 equals P2, and that's usually what's going to happen. And so usually this part of the test statistic is going to be 0. And I'm saying usually because who knows what curveball they might throw at you. So usually that one's going to be 0 because we're claiming saying, hey, there is no difference between the two proportions. And then right below you have your statistic when it comes to the standard deviation. You have your p hats of c, which is this formula off to the side. So you can have the general idea of how we deal with significance tests, and you see that all highlighted in orange. I would primarily say you're most likely, when you're dealing with two samples, going to be using this orange one, the p hats of c, and you're going to be plugging it in down here. Now, the reason I point that out is that is for a significance test. If we look at confidence intervals, it's a little bit different. When you have confidence intervals, you don't know the population parameter. You're trying to estimate it, so of course you don't know it. So you're not going to use p and 1 minus p because you don't know p. You're going to use p hat and 1 minus p hat. So that's the main difference. Hence why standard error, look at that star above the standard error. That's pretty interesting. It's like T star or Z star, right? To kind of help us out in the future. Weird. There is a Z star right there. So that star there is not an asterisk of, hey, go down the very bottom of the page and see what that means. No, that asterisk is meant to tell you, hey, if you're using these, it's your Z star or your T star. So we don't know our standard deviation. But when I'm dealing with my confidence interval, remember, it's statistic plus or minus your critical value, star. And so we have our Z star times the standard error of the statistic, the square root of p hat times 1 minus p hat over n. So that's the structure. And again, I'll zoom out and kind of scroll up. That's what our structure is. That's what we're plugging into. It's on the other side of the formula sheet. So you might need to flip or be familiar with the structure by now. And then we have, well, what if it's two samples? Well, it's a good question. If it's two samples, you're going to use the p hat 1 times 1 minus p hat 1 divided by n, then add p hat 2 times 1 minus p hat 2 divided by n. That's the standard error of the sampling statistic. Now, how is this different than this? Well, one of them does a combined proportion. Because our p hat sub c, the combined sampling proportion, is an unbiased estimator for that population. Because we don't know what the population is proportion for the two samples combined are. So we're going to use an unbiased estimator for it. This is the other one. So here's the big issue for proportions. When do I use p hats of c? And when do I not use p hats of c? Well, it tells you when p1 equals p2 is assumed. So when you're doing a significance test, use that formula. If you're dealing with the confidence interval, use that formula. So here's the structure. It's the difference p hats of 1 minus p hats of 2 plus or minus your critical value. Look at that, Z star, just like it says right up here. Weird. And then your standard error of the statistic formula. So that's with proportions. And the main thing I want you to get is what's your statistic. You can see them highlighted in pink. And, what's the difference between confidence intervals and significance tests? And that's what a lot of you are going through. How do I know when to use p hats of c? Or how do I know when to use just p hat? Good news! It tells you right there in the formula sheet. Now, the next part we're going to look at is quantitative variables. So here we are looking at sampling distribution of means. Now we're looking at this. I've already talked about it. Notice how it's set up. You have, hey, how many samples do I have? 1 or 2. Hey, do I know my standard deviation in the population? If so, there's sigma. If not, there's S. So it's broken down the same way as our inference decision-making tree. And, by the way, it's even broken down shape, center, spread, too, as well. We have our center, we have our spread. It's going to be nice for us. Now, we're going through. Remember, the idea that we talked about is when do I use which one? And notice I have a lot of T's here. Because for the most part, when we're looking at the sigmas, we're probably going to use those when dealing with finding the sample size based off what the margin of error that we're looking for is. That's really it, because if we're dealing with a confidence interval where we're trying to estimate an unknown population mean, well, how would I know my standard deviation mean then? So we're really going to be using t's for the most part on these, but it's not saying, notice I didn't say cross these out because you're still going to need them. You still have to ask yourself when you're reading, are they giving me a population standard deviation, or is this standard deviation from the sample that was collected? And that's going to tell you which direction to go. And again, you can see the setup for your mu of x bar, and then the differences, mu of 1 minus mu 2. Same idea. We'll save some time on that one. But I'm going to go through the setup for finding your test statistic. Remember, statistic minus parameter divided by standard error of the statistic. Well, if I'm dealing with t's, my x bar is my statistic, my mu is my parameter, and the standard deviation, notice I did s over square root of n, because most likely I'm going to be using s over here. And if I'm doing two sample, it's really the same idea as what I said for our z, is you're going to subtract, in this case, the sample means. That's going to give you your statistic, which, again, look, it's highlighted in pink over there on the far left side. That's your statistic, minus the parameter, and usually that's going to be 0, but it's based off with the null, again, because you don't know what curveball they're going to give you here. So usually that's going to be 0, and then you have the square roots, and you have the standard error there. Do be aware, there are so many standard deviation formulas. I've said this before, is do you think maybe they might try and trick you in some way? Maybe throw an n-1 in there or something, because you're used to that format. So become familiar with what standard deviation formula goes with which one. So this is with our test statistic. Hopefully that kind of makes sense. You see the green for the standard error, and you see the statistic in pink. Now, what if I'm dealing with a confidence interval? Well, a confidence interval has the same structure. And again, does it have it? It has the star right up there, standard error star of the sample statistic. T star, that's amazing. It's telling me to use T star if I'm in that column. Great. So it's the same idea. Statistic plus or minus your critical value from T star times the standard error, and critical value times standard error is still your margin of error. You can flip to the other page and just check to make sure I'm right with my formula. Same thing when it comes to two samples. You're going to do your statistic, which is the difference in the sample means, plus or minus. Wait a minute, we are in the standard error column, star, T star again, times the standard error of the statistics for both samples. And we have that right there for the standard deviation. So this is it for me. So yeah, there's a lot of T's and there's a lot of T stars that we see. And you may be going, well, Mr. Razor, why haven't you talked too much about this formula for sigma? And that's a good question. I've said that if you're doing a confidence interval and you don't know the population mean, then how can you find the population standard deviation? So when do we use this formula, Mr. Razor? That's, mark it down. That part's chapter 7. That's for sampling distributions. Is if I'm taking one sample and I'm finding the mean and the standard deviation, if I'm taking another sample means, and if I do that over and over and over and over and over again, that's going to give me the sampling distribution spread. And the same thing with down here. And what's the main difference between this formula here and the formula in green that we see over to the side is one's S and one's sigma. One's S, the sample standard deviation, and unbiased estimator in this case for sampling distribution for sigma. This is really it for means. A lot of the stuff is very similar to proportions, except we have T star if our population standard deviation is unknown. Now we're going to look at dealing with the inference for regressions. So here we are with sampling distributions for linear regressions, and we're going to keep a few things in mind. First off, I would write this down right now is you are not given the formula for degrees of freedom for this one. Remember, this one's n-2. For t's, remember it's n-1. I know you're going to say, Mr. Ransom, you didn't talk about degrees of freedom for t's. Don't worry, I'll get there. But do remember some of the things that are going on is the mean is going to be, for this case, it's dealing with inference for the slope. So our statistic is b. Again, highlighted in pink. It's like consistent with coloring. So our parameter is going to be beta, the slope for the population. Ooh, look at that. We get to cross off the standard deviation formulas. That's nice. So we get to cross those off. Now, do I expected to be able to interpret still? Yeah, you get to cross out the formula, but you're going to have to be able to always interpret your standard deviation, no matter which one you're dealing with. The general structure for T is right here. So if we're dealing with our statistic, which again, if we're dealing with a significance test, we're going to have our T equals, wait a minute, why is it T? Go back and look at that. Why are we dealing with T here as Do we know the population standard deviation? No. So what we're going to do is we're going to use RT, and then we have our statistic B minus the null slope. This one is not, well, it could be 0, but it's going to be based off what your null hypothesis is for that statistic over SE sub B. Where's that on our formula sheet? There is no SE sub B on your formula sheet. There's an S sub B. There's no SE sub B. Well, those mean the same thing. You're going to see it on your formula sheet as S sub B. Right down next to it, SE sub B. That is the standard error of the slope. Good news, you get to cross those out. Look at that. So that's really helpful. But notice, we're going through this, and we want to keep a few things in mind. First, you will be expected to be able to interpret it. Keep that in mind. You're always going to be expected to be able to interpret your standard deviation. You're really going to be given your S sub B from the formula sheet. For us, we looked at it as SE sub B from a computer output. They might say computer output. They might say Minitab output. That's where you're going to get the SE sub B. Now, you have to be able to interpret those, but you're not going to use the formulas. And here is the confidence interval setup. It is your statistic slope plus or minus your T star, because, yep, it's in that column with the star, n minus 2. Well, that notation is your degrees of freedom. So I wrote that down there, and that's to help you, times the standard error of the statistic. So again, that's the general structure, statistic plus or minus critical value times standard error of the statistic. So we can see on the left side, down the bottom, we see our test statistic for our significance tests. On the right side, right by me, you can see the setup for a confidence interval for slope. But there's a lot you have to cross out, well, that you get to cross out here that you don't really need to know how to use, but you do have to know how to interpret and where to find them and be able to plug them in. So that is the sampling distribution for linear regressions. And if that's all the formulas. So you may go, sweet, we're done with the formula packet, but if you were to flip the page, there are a lot of tables you have to look at. So the first table in your table packet is looking at table A, which is used for Z's. How do I know table A is used for Z's? Good question. Maybe we shouldn't ignore the picture that's on the top of the table. It tells you what statistic it's used for. That's nice. It also shows you a shaded region, which tells you every value in this table down here on the inside represents the area to the left of that test statistic. If you want an area to the right, you have to do 1 minus your table A. The first part, this first page, deals with the negative z-scores. The next page deals with the positive z-scores, and it's the exact same. Area to the left is shown in the table. If you want area to the right, you have to do 1 minus. So don't ignore what they're giving you here. It's something so simple, but it even tells you when do I use table A with z's. It shows you there. So also, you can, if you paid attention, I had 2 things highlighted here. Right here, you can see this 0.7486 is highlighted. And if I go back to the previous page, right here, you can see the 0.2514 highlighted. Hopefully, you caught those. If not, I'm going to quickly pull them up again, 0.2514 and this 0.7486. Now, why? Oh, why, Mr. Rainsberg, do you have those highlighted? They seem really close to something, don't they? I mean, this one is really close to 0.75. This one, 0.2514, that's really close to 0.25. It's like those are your first quartile and your third quartile. I'm pointing this out is 0.67, positive, negative, are good estimates of your quartiles, Q1 and Q3 for a Z. So it's nice is it's 0.67 for both of them because it is symmetrical for it. So I kind of pointed those out just to kind of give you something to maybe if you can memorize, something to keep in the back burner when it comes to how do I want to do quartiles in my Z's. 0.67, positive, negative are your first quartile and your third quartile to help out. Now the next table is going to be table B. Now if I look at table B, when do I use table B? Again, great question. It tells us we use table B when we're dealing with T's. Awesome. So it tells us when to use each table, but this shaded region looks a little bit different because it's shaded on the right side. So a table B gives us area to the right. So if I want area to the left, I'm going to have to do the 1 minus in that case. One other thing to keep in mind here is degrees of freedom. I remember I told you you're going to say, Mr. Anderson, you didn't talk about degrees of freedom with T. You did when it came to inference for regressions, and it's because I was saving it for this. And if we're looking here is your degrees of freedom column. When you have one sample, your degrees of freedom is n minus 1. When you have two samples, you have a few options for your degrees of freedom. You have n minus 1 for both samples, and you choose the smaller of them. Or you can use your calculator. Those are the two options. Now, the one thing you need to keep in mind is be consistent. If you're going to use the calculator, degrees of freedom, you better be consistent and use the calculator for everything. If you're going to use table B for degrees of freedom, then you have to be consistent and use table B for everything. You can't jump back and forth based off of what's easier in each step. It's you pick a path and you stick with it. So those are your options. Also, to keep in mind, you're going with degrees of freedom. That's nice. 1, 2, 3, 4, 5, 6, 7, 9, 10. Goes all the way down to, oh my goodness, it jumps 30, 40, 50, 60, 80, 100. It jumps all the way from 100 to 1,000. So beware the gaps in table B. You need to round down the degrees of freedom. Now, notice I said round down. Now, the reason why I went up is because when you're rounding down at the table, you're actually going up. So keep that in mind. Also on the very bottom, I have this highlighted. What about that infinity symbol? Why is that there? Because that's your Z star. And what's really nice, at the very bottom also, tells you your confidence levels. So we can see our confidence levels associated with the T values. Because, wait a minute, what does this represent on the top then? That's the tail probability. So if I have 0.025 in a right tail, then that means I am dealing with a 95% confidence interval because the right tail has 0.025 and the left tail would have 0.025. 95% confidence interval for a two-tailed. So confidence intervals are also located in table B. So when we're dealing with T's, we need to keep in mind our degrees of freedom. When we're looking at our Z's for table A, we need to keep in mind what's going on here. Also, notice I said these are highlighted, the 0.2514 and so on for the Q1, Q3. That also brings in mind that what do these numbers represent on the inside of table A? They are also your percentiles. So if I wanted the 25th percentile, I would use negative 0.67. So these are also a way to find percentiles in table A. The last table that we have is our chi-squared statistic. Just like table B, it gives us our area to the right. Now, when do I use table C? Great question. It tells you in the table because it has a chi-squared at the bottom. And it gives us the area to the right, just like our table B did. So we're going to keep that in mind. Also, our degrees of freedom. There's a few degrees of freedom formulas. When you're dealing with goodness of fit, it's number of categories minus 1. If you're dealing with homogeneity or independence and association, you're dealing with number of rows minus 1 times number of columns minus 1. So those are two different formulas. One's for goodness of fit, one works for both homogeneity and association. But there's our table C. Again, that's going to give us our degrees of freedom. We have our tail probability that's given to us, and we could go from there. One other thing that goes in mind is the larger the chi-squared statistic, the more evidence of the observed against the expected. Because remember, the formula for chi-squared is observed minus expected. So the larger the chi-squared statistic, the more evidence of the observed alternative hypothesis against the expected null hypothesis. So do you see how I phrase that? The larger the chi-squared statistic, the more evidence of the alternative hypothesis against the null hypothesis, dealing with how we state significance tests. So our chi-squared, not too much there. What would happen is you would find inside the table what's your chi-squared statistic. And so I'm just going to zoom in right here. What if my chi-squared statistic happened to fall in this row, which means that I'm dealing with a degrees of freedom of 12. Well, I would say my p-value is between 0.01 and 0.02. That's how we use table C as a quick refresher. The other way we can use table C is what if I have, oh man, there's those gaps again. So we have to keep in mind, we need to be aware of those gaps and we're going through it. So if I have degrees of freedom of 45, I'm going to round down to 40. So we're going to have the same idea with table C as we do with table B. But these are the tables. Table A, we have for our Z, we have table B for our T, and we have table C for chi-squared. How do I know? Because it shows me in the diagram. And so that is all of your formula sheet, the formulas and the tables. Be confident, be 95% confident going in there where to find the right formulas, where to find the right information based off the prompts that you are given. And good luck on the exam.